All right, for this problem, we kind of have multiple steps. We have a solution, and then we have a redox reaction, and then we have a challenge question. So I'm going to try to break it down through each one. The first one is you have a solution, a 100 milliliter solution of 0.230 molar of AgNO3, silver nitrate, and it's poured into a beaker, and then it's going to react with iron itself. The first one is asking how much NO3 you have. So you first want to find out how many moles of AgNO3, silver nitrate, you have. So remember, for dilutions, you have molarity is equal to moles over volume. In this case, it's going to be 0.230 molarity is equal to moles over the volume. And just remember, this is in milliliters, so we want it in liters. And we try to keep all the sig figs. So 0.1, 1, 2, 3, 1, 2, 3. So now we have 1, 2, 3, 4 sig figs liter. We're going to multiply it. So we should get N is equal to 0.0230 moles. Okay, so that's how much moles of AgNO3 we have. Now, that means we have, I guess the best way is this. We have one AgNO3, so that means we have one Ag, one NO3. So if we're just asking for NO3s, it's the same thing. If we have 0.023 moles of the whole thing, we're going to have 0.0230 moles of NO3. So just think of it. It's just one part of a whole. So you have one of you. How many heads do you have? One. So if there's two of yous, then you have two heads. If you have three of yous, you have three heads. If you have 3 moles of you, then you have 3 moles of heads. In this case, it's 0.023 moles of NO3. The next one, you have an iron nail that's placed into the solution. We want to know the reaction. So we're going to ignore the 6.25 for now. We're just going to write down the reaction that's going to occur. Eventually, I want the net ionic equation, but for me, it makes sense to do the molecular equation first. So we have iron, and we're going to place it into the solution of AgNO3. And we're going to make something, right? Iron is a solid. AgNO3 is an aqueous solution, and we're going to place it in here. Well, what's going to happen is you're going to have a single replacement reaction. So if a reaction is going to happen, iron and silver are going to replace each other. If they don't, then nothing happens, but obviously something happens, so they're going to replace each other. So I'm going to have silver by itself as now a solid, and then I'm going to have Fe with NO3. Now, if you look on that little sheet, you'll see that there's a +1 right here because we're looking at the net ionic rate equation. I know nitrate, it is -1, so that kind of makes sense. Here, I got a little 2+, so I know iron's a 2+ here. So the iron 2 nitrate. So that means I need 2 of these to balance it out. And then 1 iron. So here is my equation. I'm going to make sure I'm going to balance my equation really fast. Let me pull up, just make sure I'm doing it correctly. So I want to make sure that I have the right amount of stuff. Here I have 2 nitrates, so that means I need, let me change the color so we're good. 2 here, so now I have 2 nitrates, 2 here, 2 Ag, so 2 Ag here, 1 iron, 1 iron. So I have now a balanced equation that is molecular. Now let's do total ionic equation. So pretty much what that means is anytime you see, I forgot to add it here, aqueous, you're going to write it as ions. So iron is not an ion, so we're just going to keep it as is. We're going to have 2 silver ions, aqueous, 2 nitrate ions, aqueous. Here the silver becomes solid. We have 2 of those. And then we have 1 iron ion. And then 2 nitrate ions. Okay, so here is my total ionic equation, and what you're going to do is you're going to get rid of the things that are the same on the left and right. iron here is a solid, iron here is an ion. 0, 2 plus was not the same. Same thing with silver. You have +1, 0, but what's going to be the same is the nitrate. So we don't have to write it out. So the net ionic equation is going to be Fe solid plus 2Ag plus aqueous 2Ag solid plus 1 iron 2 plus. Okay, so here is my net ionic equation, and I don't think I've ever explained this before, but these coefficients are important. 1 iron is reacting with 2 silvers to create 2 silver solids and eventually become 1 iron ion. All right. Now, this is just an answer or a question about spectator ions. If this reaction happens, we're consuming all the silver and changing it all to silver solids. So in the end, we're going to get 0 silver ions. Since nitrates are not reacting, they're spectators, we're going to still have the same amounts. We started with 0.0230 moles. We're going to end up with 0.023 moles of NO3. Okay, so this is just a question of spectator versus what's being consumed. The challenge. All right, so if we put this in there, we want to find out, okay, well, some of the iron is going to react and become iron ion, or part of iron 2 nitrate. So we want to find out how much is still iron. Well, we could do that. If we know how much silver, we could figure out how much iron. Now, if you look back to the first one, here's the ratio. 1 iron reacts with 2 silver nitrates. And we could do the same thing. Instead of saying 1 molecule, we could say 1 mole. So 1 mole of iron reacts with 2 moles of this. So it's a ratio of 1 to 2. So if we have 0.023 moles of silver nitrate, in order for all this to be consumed, I need, if this was a 2 coefficient, I need this divided by 2. So pull out my calculator, 0.023 divided by 2. I need, in order for this reaction to happen, I need 0.0115 moles of iron to react with that, to create whatever I want, right? It's a 1 to 2 ratio, right? That's how we're going to figure it out, 1 to 2. Well, if I need this many moles, I can figure out the mass of that, right? I'm going to consume 0.0115 moles of iron, I could figure out the mass by multiplying by the molar mass. So we need to pull out the periodic table. If you look it up, I'm going to look at my cheat sheet and look at my answers. The molar mass of iron is 55.85 grams. So 1 mole of iron is equal to 55.85 grams. Let me keep my cheat sheet open so I can have a reference point. So here the moles cancel out and I'm left with grams. 0.0115 times 55.85 equals 0.642275. A big number. Okay, now we start off 1, 2, 3 sig figs. So I'm just going to end with 3 sig figs. Even here, it's still, we're never going to measure out to the thousands. But we consume this much. So if we want to know what's left, all we have to do is subtract. Let me try to get a different color so it's not too confusing. 6.25 grams subtracted by 0.642. And we are going to have 5.61 grams left. Okay, so I'm going to round off to the hundredths place because that's my least accurate. And there we have this problem. So kind of complex, a lot of cool concepts here, and we can actually figure out how much is going to be consumed by just how much moles of AgNO3 we actually have. All right, for the next one, we have the following equation that's given to us. We have chromium oxide, but Cr2O7, 2 minus, so it's an ion. We have iodine, ion, or iodide. We have hydrogen ion, or hydride. And then we have the following equation. So one thing that we want to pull from this is not only oxidation numbers, but also notice that the balance equation. So one of these is going to react with one of these, which is going to react with 8 hydrogens to create 2 of these, 1 of these, and 4 waters. So remember, this is just a recipe of what's going on. It's a ratio right here when you balance the equation. You could put any units here and it'll work, meaning by number wise. Grams won't work, but you could do moles. So if you go from ratio, you could go directly to moles, and we're going to do that later. First, let's assign some oxidation numbers. So should I write the rule somewhere? I guess so. So I'll really quickly, sum is equal to charge. 2, fluorine is -1. 3, hydrogen is +1. And 4, oxygen most of the time is -2. All right, so here, most of the time, oxygen is -2. So that is going to be its oxidation. And we want to find the oxidation of chromium. So 2 times 7 is 14. Now, the sum is going to equal to the charge, which is -2. So something plus 14 has to be -2, and that is 12. So 12 plus 14 is -2, +12. We have 2 of these, so it's going to be +7. So that's the oxidation number of these 2, plus 7, -2. For iodines by itself, you do have a charge of, when we say -1. Hydrogen is by itself, and it has a charge of +1, so we're going to say +1. Here, 3 plus. Here, we actually have to do some work. You have oxygen, which is going to be -2. We have 3 of them, so 3 times 2 is going to be -6, which is going to be equal to -1. So something -6 has to be 1. In this case, it's going to be +5. So iodide is going to be +5. And then you have water, which we should know by now, by -1 and 1. So now let's look which ones are going through oxidation, which ones are going through reduction. You want to see if they're going to change their oxidation state. This one's going from +7 to 3 plus. So this one is gaining electrons, gaining electrons, and so this one's being reduced. Okay, iodine is going from -1 to +5. So it is losing electrons, Leo, which means it is oxidized. So that's how you do it. Oxygen stays -2 both sides, so it doesn't do anything. Hydrogen stays +1 on both sides, so it also doesn't. So this is your redox reaction. All right, for B, let me make sure I got this right. Had the above been a total ionic equation, 5 NO3s will have been included on both sides, but since they are spectator ions, we got rid of them. When considering the Lewis structure for nitrate ions, let's figure out what it looks like. So if I want to draw the Lewis structure for this, all right, so remember, S is equal to N minus A. So that's shared electrons is equal to noble minus actual. So I have NO3. So nitrogen, if you look at the periodic table, has 5 valence electrons. Oxygen has 6 valence electrons. Remember, we want to get to an octet, which is going to be imitating noble gases, 8. And in this case, we have 4 molecules. So, or sorry, 4 atoms. So we're going to have 4 of them trying to reach the noble, which is 8. So 4 times 8. If I could do my math. 20. Oh my gosh, I can't do it. Okay, I'm sorry. It's late. I'm tired. 4 times 8. 32. All right, we want to find the actual. So nitrogen has 5. And then we have 3. Oh, I forgot. Since there's a minus, we're going to have 1 more. So we have 1 of these, 3 of these, and 1 of these. So that's 5 plus 3 times 6 plus 1. And that gives us 24. So if you do that, it's late. I can't do math. 32 minus 24 is 8. So that's 8 shares of electrons or 4 bonds. Okay. We want to try to make this symmetrical. That's usually how atoms like to be. So we're going to draw it like this. Now, I'm okay if you draw it like this. Later on, you'll know that this is the more correct one, but this is perfectly fine. 1, 2, 3, 4, 5, 6 shares. So we're going to add 1 more pair to reach our 4 bonds, and that's what it is. Now we're going to figure out all the lone pairs. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And then nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So here we are satisfied. This whole thing has -1 charge. And if I wanted to make sure I got everything correctly, let me count each pair. 1, 2, 3, 4, 5. Oops, keep adding a dot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times 2 is 24. So we got the right amount. So this is the Lewis structure of the 2. All right. This is another ratio. So I have 0.23 moles of this, which is going to react with 2.23 moles of this. And how many of this? So this is 1, 1, and this is 8. So that means 1 of these and 1 of these are going to react with 8 of these, or 1 mole, 8 moles. In this case, it's 0.23, 0.23. So it's going to be 8 times 0.23, which happens to be, I'm going to look at my cheat sheet so I don't have to do the calculations, 1.84. Also reacts with, that doesn't make sense. Produces, I'm missing something. Let me check. Oh, anyway, whatever. But let me just cross it. I think I wrote it down wrong. Anyway, how much H2O will be produced? You're looking here, 4. So the ratio is 1 mole, 1 mole, 8 mole, 2 mole, 1 mole, 4 mole. So if we start at 0.23, 4 times 0.23, and that's going to be our product. I'm looking at my cheat sheet, 0.92. Okay, so that's what you have. Remember, the coefficients are a ratio of what's going on, and we could do that by that. So hopefully that makes sense. All right, for the next one, number 3, we have a lead acid battery from a car. You have, eventually we'll actually do the lead acid battery, but you have lead and then lead oxide. It's going to be put into sulfuric acid, and you're going to produce lead sulfate and water. It's actually 2 half reactions, meaning 2 reactions are happening at the same time. The lead prong, or one of the nodes, is going to create lead 2 sulfates, but then the lead oxide is going to produce lead 2 sulfates. So we're going to have 2 reactions happening at the same time, and we want to know which one is being oxidized, which one is being reduced. So lead, if we look at this one, which is right here, lead is Pb, so that one has a charge of 0. Lead 2 oxide here, this was -2. So 2 times 2, that makes this one positive 4. So this one is +4 and -2. They both will react with sulfuric acid and create the same product. But you'll notice that they're going to have different oxidation reductions. Here we have PbSO4. Sulfate has a charge of 2-. Now that's kind of the key here. This is a ionic polyatomic, so since this is 2-, let me just make sure I'm correct. Since it is 2-, that's going to make our lead 2+. So what's going to happen is here it's going from 0 to 2+. So that means it is losing electrons, Leo. So that means it's being oxidized because it's going from 0 to +2. And in this case, it's going from +4 to +2. So it is gaining electrons reduced because it's going from +4 to +2. All right, let me just make sure I covered everything, and that's actually what's happening. So yeah, so the lead metal is being oxidized, and then the lead 4 oxide is being reduced. All right, our next one, B, we have the following. It is not balanced, so let's balance it out. All right, this one is kind of difficult, and the reason why it's difficult because I normally like to save hydrogen and oxygen for last. Now the problem with that is here the nitrogen is attached both with the hydrogen and the oxygen, so it makes more sense in this case to go backwards than what's logical. So I'm going to try to balance out the hydrogens first and then try to see if that's going to match up my oxygens and then finally do my nitrogens. And normally it's because I like to do oxygen last because it's attached to many things, but in this case nitrogen is attached to 3 things. And you have one with H, one with O, and one with itself, but it's a Hofbrinkel diatomic, so it makes it a little bit more difficult. So we're going to do it the illogical way. Okay, I'm going to do H first, O, and then N. All right, 3 here and 2 here. So I'm going to have to find a common multiple, 3 and 2, and to kind of see where we get. So 3 times 2 gives me 6, 2 times 3 gives me 6. Let's see how close we are with oxygen. 3 times 0 gives me 3. Have another here, which is 2. So I need to find a multiple again. So in order to make this work, I'm going to double this, make this a 6, and then kind of just start all over again. So I'm going to erase this, erase this, erase, erase. All right. So if I said 6, so I have 6 times 2, which is 12. That means I need 4 of these. So let's see if that works. 6 times that is 12. 4 times 3 is 12. 6 times 0 or 1 is 6. That means I need 3 of these. All right. So 3 times 2 is 6. So right now we're balanced with hydrogen and oxygen. Let's see if we got lucky with nitrogen. 4 plus 3, which is 7. Here we have N2. So you could kind of cheat. We want 7. Since it's a diatomic, you could do that. So you could do 7 over 2, and it will work. But if you really don't like that, you could also just multiply everything by 2. So if I multiply everything by 2, I need 8 of these, 6 of these, 7 of these, and 12 of these. So whichever one kind of works for you is fine. I'm going to stick it as the pink because that's the more simple version because the numbers are a little bit smaller, but it's either pink or yellow, they're both fine. But that's how you balance it. This one was hard, and the reason is because the nitrogen is attached to a bunch of things. Attached to the hydrogen, attached to the oxygen, and then it's a diatomic, which has to make it an even number. So normally, like I said, I would have done nitrogen, hydrogen, oxygen, but in this case, it would have been easier to do hydrogen, oxygen, nitrogen. All right. All right, for number 4, we have SO2 2-, and we want to find the Lewis structure for that. So we're going to use S equals N minus A. So when you're looking at this, sulfur normally has 1, 2, 3, 4, 5, 6. Oxygen normally has 1, 2, 3, 4, 5, 6. And we have 2 of these. I'm going to draw it out. And then in the end, we have a 2 minus charge. So that means we have 2 extra electrons at the end. So that's kind of what's going on. We have sulfur 6 valence, oxygen 6 valence, oxygen 6 valence, and then 2 extra electrons at the end. The noble form doesn't really matter. So we have 1, 2, 3 things. So it's 3 times 8. So if I could do my math in my head still, it is 24 minus the actual. In this case, it's 3 times 6. So that's 18 plus 2, which is 20. And if I want to double check, I could just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that means I'm going to have 4 shared electrons or 2 bonds. Okay, so we want to make it symmetrical. So sulfur is going to be in the middle. You're going to have it like that. And now we're just going to add electrons. Oxygen sharing 2, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that is my Lewis structure of SO2 2 minus. I could make sure I have the right amount of electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs or 20. So I am good. So I have 2 single bonds. 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, 8 lone pairs in this structure. All right, for the last problem, we're going to have the following. We have CS2, 3O2, CO2, 2SO4. So there's 2 things that we want to know. First is the structure of SO4. I believe I'm going to make sure I'm doing it correctly. No, SO2. Oh, this is SO2. Did I get them mixed up? No, I just wrote it wrong. SO2. So first we want to find the oxidation numbers and figure out which one's being reduced and oxidized. Then we want to find the structure of SO2. Let me just make sure that is correct. Maybe for all of them. All right, maybe for all of them. All right. So let's just do it. So we have the following. We have carbon and sulfur. Sulfur is going to normally be a charge of -2 because it's very similar to oxygen. So 2 times 2 is 4. So that means in this case, copper is going to, or not copper, carbon is going to be +4. Here oxygen is with itself, so it's going to oxidation number of 0. -2 times 2, so this case is going to be +4. And here we have -2 times 2, so in this case sulfur is going to be +4. They both should be electronegative, but since oxygen's more, it's going to suck the electrons from sulfur, so that's why sulfur is going to be the positive in this case. So when we're looking at it, carbon actually stays the same, +4 +4. Sulfur is going from -2 to +4, so it's going to gain, or sorry, lose electrons. And oxygen is going from 0 to -2 on both cases. So in both cases, oxygen is gaining electrons. So let me just make sure I'm answering the questions. Turn on my other computer. So in this case, since it's gaining electrons, oxygen is being reduced, and then sulfur is being oxidized. So sulfur is going from -2 to +4, so it's losing electrons, so it's going to be oxidized. And then oxygen is going from 0 to -2, so it's gaining electrons, so it's going to be reduced. And I believe I answered the question, so yeah, oxygen is being reduced, sulfur is being oxidized. Now we're going to look at the SO2 molecule over here. Okay, in this case, oxygen is more electronegative than sulfur, so it's going to suck the electrons closer to it. but we still want to know what it looks like. So we're going to use the equation S equals N minus A. So remember, sulfur has 1, 2, 3, 4, 5, 6. Similar to oxygen, 1, 2, 3, 4, 5, 6. We just did SO2 2 minus, but this time we're going to do SO2 with neutral. So that's what it is. So we have 3, and they want to obtain an octet. We have 3, and they actually only have 6. So 3 times 8 is 24. 3 times 6 is 18. So we're going to share 6 electrons or 3 bonds. So S, O, O, and then we're going to add 1 more because we need it. Here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6. Yeah. So here is our Lewis structure of the following thing. And O2 is going to be similar to CO2. I think that's it. Maybe all of them. All right, let's do all of them then. So for CS2, we have carbon, which is 1, 2, 3, 4. Sulfur, like I said, is like oxygen, 6. So if we're going to use the equation, noble is 3 times 8, which is 24. Actual is 4 plus 6 plus 6, so that's 10, 16. So that means when we subtract it, we're going to have 8 shared electrons or 4 bonds. So it will look like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep, so it'll be like that. The next one is O2. Okay. I could just cheat because it's the same, so they're just gonna. And what's easy about O2 is both of them has a lone pair, so if they're gonna share 2, you just connect those 2 dots. But you could do it the long way. And the last one is CO2. I'll do it over here. CO2. So we have carbon 1, 2, 3, 4. Oxygen 1, 2, 3, 4, 5, 6. The numbers are going to look exactly like this. So there's going to have 8 bonds, 4 together. So again, it's going to look just like CS2, but it's going to be CO2. Okay. All right. If you have questions, email me. Other than that, take care.